Good morning, everybody. I'm glad to welcome you and on another or next session, System Engineering, Computer and Technology. My name is Renát Haluška. I'm from Technical University of Košice, and I will be the chair of this session. Every participant has 80 minutes for his presentation. The best is 15 and 3 minutes for questions and answers. The first presentation, a hybrid random number generator based on chaos optimization and linear feedback shift register. The presenter is Fatih Ozkaynak from Turkish. So welcome, and the floor is yours. Yeah, okay.
Hello everyone, my name is Fatih Özkaynak. I come from Turkey, Fırat University Department of Software Engineering. My research area related to design and analysis of encryption system. In this study, we focus on the cryptographic randomness. We generate a new hybrid random number generator based on chaotic system optimization algorithms and deterministic random number generator. I would like to start with the presentation outline. Firstly, I will give some basic information about chaos theory, cryptography, and random number generator. Then I will talk about details of the proposed method. Next, I will show analysis result, and finally summarize the study. Our daily lives in many services are being moved to digital environment. Artificial intelligence, Internet of Things, big data, industry 4.0, very important concept. But information in the digital environment poses a great risk. Therefore, security of this information is a necessity. Maybe first solution to ensuring the security is the cryptographic systems. Cryptology is a science involving in mathematics, electrical engineering, and computer science. It is a hot research topic. Therefore, many researchers proposed many encryption algorithms throughout the history. Maybe one of the most known is the Caesar encryption algorithm. The design logic of the Caesar encryption algorithm is based on the shifting the letter according to case value. For example, is the key value is 4, hello world sentence is encrypted as this string. Every letters shifting the 4 position. Another important topic constitute to study is the chaotic systems. Chaotic systems a study of nonlinear dynamical systems. It is a sensitive to dependency to initial conditions and control parameters. Therefore, these systems does not the predictable. This property is very important for cryptographic systems. We use these properties and using chaotic system as an entropy source. Dependency to initial conditions and control parameters properties proposed Edward Lorenz. He is a mathematician and methodologist who was invented the butterfly effect. He showed that flap of butterfly's wings cause a tornado. Chaotic systems have many application areas in science and engineering, especially in computer science, determining of optimization parameter, prediction of time series, simulation modeling, and secure communications. Some of application area of these fascinating systems. There is a strong relationship chaotic systems and requirement of the cryptographic systems. sensitive dependency to initial conditions and control parameters are connected to confusion and the diffusion of the informations. There are two main research topic in the literature based on chaotic systems for cryptography. One topic is related to chaotic permutations. Another topic is the chaotic generation of the chaotic case. This study focuses on the generation of chaos basic randomness. Random numbers important properties in science and engineering, especially information security area. We use randomness many subfield. For example, encryption case, signature parameters, masking values, and initializing vectors. Quality of the randomness is directly affect the security of an encryption algorithms. Therefore, robust randomness very important for security researchers. And idle random number generators should all admissible values equal probability and unpredictable nature. We guarantee these properties and chaotic systems and optimization algorithms. In the literature, there are two main category for random number generators. These are deterministic generator and true random number generators. There are several advantage and disadvantage these categories. In this study, we combine these advantage properties, these two sub classes. We use both deterministic generator and true random generator. This is the problem. We how to combine these two generators. In this study, we use linear feedback shift register as a deterministic random number generator. This is a simple structure. Therefore, it is a very cheap and very fast. But it is an important problem. This is a deterministic and totally known feature random values. We need to several standards to show the quality of this randomness. Therefore, we use different tests. For example, NIST randomness test. But NIST randomness test require to 1 million bits. Therefore, we need to huge parameters for linear feedback shift registers. But this time we need to MP problem because there is a many configuration parameters. We solve this problem using optimization algorithm. This figure shows that our architecture for proposed hybrid random number generator. Actually, we use different deterministic random number generators. Only in this study, we use the linear feedback shift registers. And aim of objective function, our optimization algorithm is the NIST test. So by this way, we guarantee of the statistical quality of the deterministic random number generator. We generate many random numbers configurations, and we put it the entropy pool, and then we select these values using chaotic systems by this way, we guarantee statistical quality and unpredictable structure of the generators. In this paper, we determine 471 different parameters of linear feedback shift register. Uh, Firstly, using optimization algorithm, we publish this data set with this paper publicly for all researchers. And we publish all configurations, we publish all analysis result for all determined initial conditions and control parameters. Actually, we have many configuration parameters, but only 471 configurations satisfy the all needs test. This is some example of this analysis. We not only needs randomness test and analyzed different aspect of the randomness. For example, key sequence test, autocorrelation, and entropy tested. In this study, we show that optimization algorithm, this is a important advantage determining of the deterministic random numbers configuration of the deterministic random number generators, and get results show that statistical properties suitable for statistical requirement, and generated random numbers pools selected using chaotic systems, and these properties have to robust unpredictable natures. In the future, we try to different selection procedures, different optimization algorithms, and different deterministic random number generators, and we plan to use this randomness design and combination of different encryption algorithms. Thanks so much.
Many thanks, Mr. Fatih. So, maybe I have some questions. What are the potential practical application of the proposed architecture in IoT industry 4.0 or NI, from your opinion?
Cryptographic randomness, important part of these applications. We propose many personal information in the artificial intelligence industry 4.0. This information encrypted using personal case. In our maybe this architecture, you select a personal case using your options. There is a strong entropy pools satisfy statistical randomness, but any attacker get this information attack to any systems, but you select only a personal case using your informations. Maybe these systems in practical side use determining your encryption case.
Thank you very much for
You're
your
welcome.
answer. Any questions? No? Okay, thank you very much.
You're welcome.
I think that we can move on. As I know, the Next presentation, NFT Cryptopunks generation using machine learning algorithm with the president Rashid Aurangzeb from Saudi Arabia should be online. Yeah,
Yeah, I'm here. Hello.
stage is yours.
Yeah, thank you so much.
Yeah, but
Sorry, just give me a second. I'm not able to like share my screen.
because yeah, it looks like that. Searching the button for sharing.
Uh, I'm not able to share the screen. Uh, shall I share my PPT with you and you can share it? Is it possible?
Not sure. Do we have a presentation somewhere? No. Maybe.
Yeah. I have shared the PPT here in the chat. I've shared in the chat. Didn't you get it? It's sent from my side.
Okay, so I supposed to that we can fix these technical issues and maybe Mr. Artur Alonso from Hungary can present. Is it okay for you?
Yeah, sure.
Okay.
Just give me.
So the next presentation is assistive robots, a user-centric evaluation framework for human-robot interaction systems. The presenter is Artur Alonso from Hungary. Welcome, and stage is yours.
Good morning. I'm Artur Alonso. I do mechatronics engineering at the University of Debrecen. I have been working with assistive robots, and I'm here to present to you the user-centric evaluation framework we came up with to analyze the human-robot interaction systems. So, outline of the presentation, first the motivation for this research, an introduction to what are these assistive robotic systems, what are the indicators of the human intent that enable us to communicate with the robots, this criteria evaluation system we came up with, and we're gonna go through some case studies to analyze them, so see the final scores and the takeaways from this research. So firstly, my personal motivation, I have a background in engineering and neurophysiology. I'm working with control system for prosthetics to help these people with physical disabilities. For example, Stephen Hawking had to use a smart wheelchair because of his disease, amyotrophic lateral scoliosis, ALS, that impaired his movements. And using these robotic systems, he was able to interact with the road and keep his work. Well, other very interesting disease, if may I say, is the locked-in syndrome. It's a disease that the patient cannot walk, cannot talk, can just move it their own eyes. And it's a challenge to make a system to cope with it and enable these people to go back to their normal living. And at last, my field of work is with amputees, that we can give them back their arm or leg in a robotic version with improvements, and how can we control it. So the biggest motivation here was, while I was doing this neurorobotics part, we lacked a way to evaluate different systems and compare them directly to see what are the improvements needed on nowadays technology. So here we have some example of assistive robots. Just a second. Walking dog, robotic dog for visually impaired people, healthcare personal assistant, and a smart wheeler. And those robots are specialized systems that are designed to aid individuals with disabilities or limitations, right? So how do they work? They always start on the user. And this is the user-centric approach we want to provide. That is how the user is going to provide this human intent to the assistive device by means of the interface and their sensors, that we also provide the feedback to the user by the user interface. And this assistive device, if all the programming and the controllers work properly, will create an effect on the environment that by itself will provide a feedback to the assistive device through its sensors and also to the user. And where is this human-robot interaction we are talking about? It's right here between the user and the interface. This is the scope of our analysis today. So I want to advocate for 5 main ways to get the human intent from the human to the machine, that are the mechanical, the vocal, the visual, the mental state-based ones, and the muscle contraction-based ones. We're going to see them on the case studies. So to analyze these systems that are very different, we searched the literature, and there are different criteria, and none of them were in a framework with different approaches. So by focusing on the user experience, we came up with these 5 criteria where a score of 1 on each one of them would be the poorest system, and the score of 5 would be the highest. So to start with, the first criteria is the accurate information rate. It's based on the transfer information rate that was widely used in the literature. But for example, if we have a camera with computational vision, but its focus is shifted, the accuracy of this measurement would be low. So we take this information transfer rate and then multiply by the accuracy of this interface, and we get the C1 criteria by normalizing the curve of the systems evaluated and scoring them from 1 to 5 according to its quartile. The second criterion is the level of naturality of this system. That is how close to the human-human interaction the human-robot interaction is. And this is very important in a physiological point of view, as every time we do something differently, for example, if I have to press buttons on my hand to move my robotic hand, it's unnatural, and it will make your brain confused and start to haywire the neurons that can lead to possible problems in the future. The third criterion is the learning curve. That's how much time and effort you have to put so that this interface works properly with you. For example, a voice-based system would be super intuitive that you can just start speaking with almost no learning curve, while a manually driven car requires a high effort to be used. Well, C4, the reliability and required calibration, represents basically the amount of time we will have the device but won't be able to use it. Can be because of downtime, can be because of network connection, can be because every time you change the user or change the place, you require new calibration. So different systems will have different reliability scores. And the focus here on C5, it's again on the user and how this person will access it. For example, if you give to a blind person a visual interface with just visual feedback, no audio, no tactile feedback, its accessibility score will be 1, as it will be useless for this person. And this is the user-centric point of view. Well, the highest level of accessibility we have nowadays would be the ones based on the inner mental state using electroencephalography techniques to understand what is your thought, roughly speaking, and make the robot act accordingly. So the total score is basically the sum of all those criterion. Let's see the case studies for each one of these intent sources. So firstly, the external mechanical displacement, as we can see here in the smart wheelchair on this paper, uses a joystick to control the direction. And while analyzing it, again, its accessibility score is the lowest because you need to use your hand movement and put some effort to do that, so wouldn't be suitable for a paraplegic person who would say to a person with locked-in syndrome. While these kind of systems have very low downtime and, well, if the rest of the assistive robot is made well, the maintenance would be low, not any problem regarding the interface on it. But the amount of information, besides being near perfect accuracy, we can just press this button or choose a direction one at a time. So the amount of information extracted from this interface is low. Secondly, voice commands. Here we have this mobility aid robot for visually impaired people. They use large language models to understand the intent of the person. And here we have a high information rate, but a median average accuracy with a transfer ability of 1, but the highest level of naturality, as you just need to speak with it. Thirdly, we would have the body movement-based one, and this healthcare personal assistant robots. They basically react to their environment, trying to provide assistance as a nurse would. And what I want to show you here is that when we try to mimic another human in the user point of view, this would be described as the perfect human-robotic interaction system, as if the rest of the system works for the interface point of view, you would have the highest amount of information and accuracy with this totally aware system, with a highest level of naturality, as you're just acting as normal as you could, and it reacts to your needs in case you have a breathing problem or etc. Also, learning curve is none because you're just living and it reacts to your needs. The required calibration and maintenance regarding the interface itself is very low, as you can see it's based on the Xbox 360 sensor Kinect, and it can just instantaneously recognize you. And here is the thing: if the patient is in coma or in a locked-in syndrome, this robot would still work because it reacts to your needs. So if this person have a cardiac arrest, this robot would be aware of it and act as a monitoring device and act accordingly. So some specific cases, for example, is the one with eye movement tracking for patients with locked-in syndrome is very important because they can just move their eyes. So we use a camera to keep tracking the user, and it has a high information rate with a good average accuracy. And in this paper, they could do one without required calibration for every use, and etc. To the top-notch technologies we have nowadays to control proteases using electromyographic-based proteases, here we have a big problem. That's what my research is trying to tackle. There is the available technology on the research and commercial grade is very unintuitive and has a highest learning curve. As you have, for example, to contract your arm to actually move your fingers, and it's giving neurological problems to the user on the long term, while also requiring calibration and maintenance. So what would be the other alternative? Would it be the electroencephalography, EEG-based prosthetics, or exoskeletons? And here we can see a successful experiment published on Nature in 2016, where this paraplegic man could eat normally in the restaurant by using this exoskeleton controlled by his inner mental state that would have, again, a very good score. Besides, there is a big learning curve and very much maintenance, downtime, and calibration required. So with this, the overall scores you can see here, we would classify in conclusion the systems of voice, body movement, and eye movement as excellent interaction systems, the external mechanical displacement and the mental state based ones with a good interaction system, and at the last place, the poor interaction system would be the muscle fiber one for the problems we mentioned before that we are working to improve on further research. So the key takeaways from this is that we have to recognize the interface limitations depending on who is the user of our devices that we're researching for. And we can continue the improvement of these technologies by tackling multiple intent sources for those devices and improve their adaptability to different and adverse environments. And with this whole framework, we covered the educational needs on how to teach each one of these different technologies for our own students at the university and provide the research gaps that they have to strive for further work. So thank you for listening. This was my presentation. Do you have any questions?
Many thanks, Mr. Alonso, for your presentation. Very nice. So there are any questions from audience to our presenter? Okay, so I will ask.
Okay, thank you very much for your presentation. I really appreciate it very much. But I'm interested in how can you use in the future artificial intelligence like machine learning or deep learning for your research?
Okay, very interesting question. If we go here back to the accuracy information transfer ratio of most of these interfaces, they have the accuracy issue. And by understanding how does the pattern of the signals we're acquiring change using machine learning, different neural networks, convolutional, spiking, recurrent neural networks, we can understand better these patterns to actually improve the accuracy percentage and make these devices acting as intended by the user. Thank you.
Thank you. Thank you very much. Any other questions? Maybe may I ask you, I saw that you have in presentation human robot with a kid. Maybe what is the impact to Uncanny Valley? If you know what I mean, that the robot looks like too much like a human, but it's too human that it's scared. So what is the impact to human intent or
Thank you for the question. The healthcare assistant robots industry is a very, let's call, striving field right now. And yes, humans fear that other robots will take their job. And when you interact with them, what if the needle goes through your hand? So in a psychological point of view, it's very scary for nowadays people that are used to the human care, that robots might go there and start take care of them. But if you look to this kid right here, this kid is very interested on it. Like, whoa, I will have a very special robotic precise care, and he looks nice. He's smiling. So we are trying to make this how can I say, emotional connection with the robots and the humans, what can be dangerous. But it depends on us, researchers and the startup founders, to make these devices better. We have already cute little robots just to be your friend in the hospital, and now we are trying to make the surgeons robots more human friendly, let's call it. But I think it's a problem of nowadays generation, and the next alpha generation is already adapted to it.
Thank you. Thank you for the answer. Yeah.
Thank you. Sorry, can I ask you about the robotic arm you presented? I guess this one. Why does all prosthetic always look like a real human arm? Because if you would replace it with for example, some specialized hook or some specialized tool, would it change your values or your criteria? Thank you.
Okay. Well, we have some commercial available devices for handwork. So I have a person I contacted in Canada that he's actually a lumberjack. So he has a hook as his prosthetic device. And it's actually simpler because if you remove all the degrees of freedom from the hand, the control system is much more simplified. In his case, he just wanted his hook to be able to give a strike and pull the log without hurting his forearm. And there is very well adapted systems for that. So I would say this side of giving you, I don't know, a tool instead of a hand directly is already available. And what would change in this case is the accuracy, because you're not controlling anymore the hand movements. You are telling me that you want to pull something or not. It's a binary value. So this accuracy would go higher, while still it's not a natural thing that in this case, the control system they use it, you can see 2 electrodes. So you have contract up and contract down your forearm muscles. So what they are doing is some kind of Morse code. You do like up, up, down, and it will catch your intent. So it's still not natural. You still have to calibrate from use to use, person to person. But what would change would be the accuracy of this system for sure. Thank you.
Thank you again.
Okay.
So, already we have. Okay. So we can move back again to NFT Cryptopunks generation using machine learning algorithm. Mrs. Ritu, stage is yours.
Thank you so much, sir. And I'm here to present my paper, that is NFT Cryptopunks generation using machine learning algorithm, that is GCGen. A non-fungible token or NFT is a kind of digital asset basically that signifies ownership or proof of authenticity. Can I have the next slide, please? Yeah. Okay. NFT is basically a kind of digital asset that signifies ownership or proof of authenticity. of a special good or like a piece of material such as artwork, music, films, or tweets. And like this study investigates, like our objective is to how a DigiGen, that is a deep convolutional generative adversarial network, can be used to create distinctive pictures of CryptoPunks that can be converted into NFTs. Now, basically, CryptoPunks, a collection of 10,000 8-bit characters, was released by Ethereum blockchain in 2017 and became valuable NFT collectibles. And now we have used the method for like the DigiGen model on existing CryptoPunks dataset. And then we have used the different metrics like inception score and project inception distance to assess our uniqueness and image quality. And then you can see like we have like various DigiGen successfully generated high quality unique CryptoPunks potential for expanding the number of available CryptoPunks, offering more choices for collectors. Yeah, the next slide, please. Okay, if we talk about the methodology, first of all, I would like to talk about the different types of NFTs as well. The different types of NFTs that we can use are like collectible NFTs, utility NFTs, digital art NFTs, real world asset NFTs, and like decentralized finance NFTs. Then talking about the general adversarial networks, that is a deep learning architecture that was first put forth and by like I guess I'm Goodfellow and his associates in 2014. And the generator and discriminator neural networks, which make up the GAN, compete with one another to create artificial data that closely matches the real data. Talking about the DC-GAN, it's a development of the GAN architecture. Both the discriminator and generator networks are constructed using CNN model. Then now coming to the methodology, the first ever step is to collect and pre-process the data. In this, we first collect a large data set of CryptoPunks images and then we pre-process them by resizing, normalizing, and converting to a suitable format for input to a DCGAN model. Now, the second step is to build the DCGAN model. In this first, what we'll do, we'll first design and build the DCGAN model using deep convolution neural networks to generate new CryptoPunks images and that are similar to the original data set. Then further, we'll train our model. After that, using this, like in training the model, we first like using the pre-processed data set. We are trained by our model by feeding the created pictures to the generator network and the actual CryptoPunks photos to the discriminator network. Then the next step is to fine-tune the model, and this is done to increase the quality of the produced pictures. And this we can do by modifying hyperparameters like learning rate, patch size, and the number of epochs. Next, we will generate the NFTs using the trained model and by sampling our from the generator network. Then we'll evaluate and refine. We will analyze the NFT CryptoPunks that were produced and modify the model as needed to raise the caliber of the pictures that were produced. Thereafter, at the end, we'll deploy the model to generate the new CryptoPunks on demand. Next slide, please. This is the proposed algorithm that we have used in this, and theory parts we have discussed in the previous slide, and this we have just we have included to show you the practical implementation. Next slide, please. Yeah, coming to the results section, we have like taken various, we have created new punks by training the DCGAN uses the Cryptopunks dataset. And we have examined the variations in pricing among the 5 different categories of funds on the market as like male, female, zombie, ape, and alien. And from the this flow diagram, you can see like what we have observed that from 2000 to 17 to present, male punks had lower average prices compared to ape and alien punks. And this we have the data we have taken online from the cable dataset. And the prices differences, like significant variations in prices, were noted between the categories also over the period of time. Next slide, please. Here you can see the difference between the human punks and the alien punks. The bar graph shows us the huge difference between the both. Next slide, please. Here we can see the difference between the result continues, and we can see the difference between the zombie punks and the ape punks. And this is almost the similar. We can't see the much difference between the zombie and the ape as we have the like difference in the human ones. Next, please. Okay, if you talk about the generating new CryptoPunks, we have like different things, different steps involved. The first one is what is our goal? Goal is basically to analyze the model ability to generate new CryptoPunks using an existing data set. Then we have assessed it based on the visual quality, resemblance, distinctiveness, and variety of generated CryptoPunks. Based on the traits, we can study the model's ability to replicate desired traits, like based on accessories, hairstyles, expressions, etc. Then we tested the model capacity to create the new unique designs beyond the original data set. And what we find out? We find out that the highlighted model success in generating CryptoPunks, but noted areas for improvement obviously is there in visual appeal and diversity. And the key factors that we have seen here are like data set quality. The key factors that we can put on focus on is the data set quality, model architecture, and the evaluation metrics impact the outcomes there. Next slide, please. These are the various references that we have used for our presentation, for our like basically the research. Thank you so much. And if we talk about if we talk about the future scope, like there is a potential to incorporate like interactive or dynamic components into the generated CryptoPunks, enhancing their appeal like to users and collectors. Thank you so much. Yeah.
Thank you so much for your presentation, Ms. Gupta. Are there some questions?
If I'm not mistaken, you mentioned that female NFTs had a lower price when compared to male human-based NFTs. And I would like to know your opinion on if it's related to the statistics that there are more male NFTs than female, and therefore the probability of more of them being highly evaluated is higher, or there was something intrinsically related with the gender of the human represented.
Actually, in this, I haven't included that table in this one, which shows like it's worth noting that like, there is just few examples of CryptoPunk sales, and the prices can vary greatly depending on the uniqueness of the CryptoPunks and the current market conditions. So we can see that it is. It's important to understand the other factors that including market circumstances, variations in demand, and specific client preferences, it can also impact the price of human punks. And by performing the additional analysis, such as like looking into unique traits or attribute combinations, we can have a like deeper understanding of the price dynamics using cryptography ecosystem.
Thank you for your answer. Maybe I have also one question. How might the development of AI-generate NFTs impact the future of the art market and the concept of ownership?
Yeah, basically the machine learning algorithms and the NFT crypto holds like immense possibilities for the future, opening like new avenues for innovation and creativity in the realm of digital art. And further, we can say like with the expansion of the NFT, it may become feasible to introduce like interactive or like dynamic elements in the generated crypto forms, and that further increase their attractiveness to users and collectors, I think. Basically, we can say like the combination of machine learning algorithm and the NFT CryptoPunks had a great potential and presenting fresh opportunities for the artistic invention and originality in the digital art domain.
Thank you for your answer.
Okay. Thank you.
For presentation. Thank you.
Thank you so much.
The next presentation is a classifier for automatic categorization of chronic venous insufficiency images. The presenter, Mr. Talha Karadeniz from Turkey. I study at I work at Software University Software Engineering Department.
Today I will talk about our paper titled with a classifier for automatic categorization of CVI images. Actually, let me first state the details of the CVI. Actually, it's an abbreviation of chronic venous insufficiency, and its definition can be given with the veins in the legs fail to return the blood, and it occurs due to damaged valves in the vein, and over time this can cause swelling, pain, and varicose veins, famous illness, and it can lead to ulcers and skin infections. CVI has, when it comes to causes, symptoms, and diagnosis, we have that in the causes we have weak or damaged veins in the legs, and due to aging and prolonged standing and obesity. And when it comes to symptoms, we have swelling, pain, and varicose veins with skin changes. And when it comes to diagnosis, we have the physical examination, duplex ultrasound, and venography. When it comes to the treatment, we can apply lifestyle changes like exercising and weight loss, and one can apply compression stockings. One can apply medications and laser therapy, and in advanced cases, one can apply surgery. The main motivation behind our work was to produce a decision support system for doctors to diagnose CVI. And since such a condition is fatal to humanity, we have thought that this can be very beneficial. Before moving on the overflow of the overall flow of the overall algorithm, let me note some things about the state of the art and literature. In Shi et al.'s work, there is a CVI classifier proposed, and it is actually based on fitting supervised patches to to the image and constructed a sophisticated SVM, and in the result, their system outperforms the manual diagnosis of doctors. And after that, Krishnan et al.'s work come. In this work, actually, the thermal images are used, and it's deep learning based. It outperforms VGG, EfficientNet, and ResNet, and it outperforms also clinicians' diagnosis. One more work we have, it's Tanka et al.'s work, and it has used almost the same methodology at Shi et al.'s. That is training test split of 2 and 1 is applied, and but the overall in the overall 20 run average is missing. That is, in the Shi et al.'s work, there is a 20 run of experiment, the train set test split and accuracy of the average of the accuracies and other metrics are taken. But in this paper, there is only one run, and they report their one run as 1-0 accuracy. So this can be a little bit misleading. This is also a deep learning based method. When it comes to methodology and components of our system, we can talk about the first methodology. We have applied the train test split of 2 and 1, 2 to training samples, 1 to test samples, and we have applied again the Shi et al.'s methodology with 20 runs. 20 run of train test split testing is applied, and the average is taken, and we have measured accuracy, F1 score, and kappa score. After the methodology, we can talk about the components of the system, components of our algorithm. In the first place, we have fuzzy C-means. In the second place, we have particle swarm optimization. And in the third place, we have VGG16. After that, we have RFE-CV, which is a future selection algorithm. FCM is actually soft-based clustering, and it assigns belongings to vectors, and each belonging sum up to one for one cluster, one for second cluster, and for nth cluster, and these sum up to 1. These belongings are calculated with respect to the distance to clusters. And after that, we have the PSO. PSO is actually inspired by the social behavior of the swarms, and swarm examples can be given as bird flocking and fish schooling. And in the PSO, we have a set of particles, and each particle has a velocity and a position, and each particle, the update of the velocity is done according to the weighted sum of the personal best and the social best. Social best is determined with respect to the neighbor's best. So each particle is a candidate solution for the overall optimization problem. After that, we have the famous VGG16. We have used VGG16 for computer vision part of the system. It's a deep convolutional neural network, and it is presented by Visual Geometry Group of University of Oxford, and although it's simple, it is used widely in variety of tasks, and it has 16 layers. In these 16 layers, we have 13 layers of feature extraction and 3 layers of fully connected layers. And additionally, for nonlinearity, we have ReLU activations, and for the dimension reduction, we have 5 max pooling layers. Before moving on the phases of our algorithm, let me state the overall flow of the method. In the first place, we have extracted VGG deep features from each image, and we have taken these and we have fed these to RFE-CV, which is a feature selection algorithm, and we have used the implementation in scikit-learn. And these features, then deep features and the reduced features, and then fed to classifiers. First classifier first classifier is, for example, MLP, and then naive Bayes and SPM and so on. We have used several traditional classifiers, and we have also tested our own classifier. In our own classifier, we have applied two phases, fit and predict. In the fit phase, we fit FCM, fuzzy C-means clustering, to class 0 vectors, and we obtain the class 0 clusters. And we, in the second part, we applied fuzzy C-means to X1 vectors, and we obtained the cluster 1 clusters. And then we apply the particle swarm optimization to find the weights of each clusters. Actually, this part is a little bit complicated, but I will only state that in summary, after the PSO, we have weights for each cluster. So in the predict phase, when an input sample comes, we calculate the vector, we calculate the weighted mean absolution deviation of the cluster 0 with respect to input sample, and we record these values, and we calculate again the weighted mean absolute deviation of clusters 1, the clusters of class 1 with respect to the input sample, and we record these values, and we compare these values, and if the weighted mean absolute deviation of class 0 samples are less than the class 1, then we assign the sample to class 0. Otherwise, we assign the sample to class 1. This is the overall logic of the predict algorithm. Actually, we have implemented the system in scikit-learn. We have implemented in scikit-learn, and we have used the base classes of Bayes estimator and classifier mixin. You can see the overall algorithm here. And when it comes to the results, you can see that TVI classifier here is the state-of-the-art classifier, which belongs to Shi et al. And you can see that our classifier proposed method is one step beyond this. And in the proposed method, we have an accuracy of 0.931, and we have an F1 score of 0.916 and a kappa score of 0.888. And the other classifiers are the deep features followed by the generic classifiers like MLP, naive Bayes, and Gauss gradient boosting machines. These are all we have in our method. Passes this also is better than also these classifiers. So in addition to these, we have applied another set of tests to test our classifiers generalization ability. We have taken 8 datasets from a CVI repository, and we have compared our classifier with 9 different classifiers. Here you can see the names of the classifiers, decision trees, naive Bayes, support vector machines, and goes on like this. And we have compared these in metrics of F1 score, kappa, and ROC-AUG. You can see the average of these in 8 datasets, and in 8 datasets, our method outperforms the other methods. Kappa score here, ROC-AUG score here, and that's all. Thank you. If you have any questions, I will be very glad to answer.
Thank you very much, Mr. Kadermitz, for your presentation. And I open the question session. Yeah.
If we can go back to the feature extraction and the cluster, soft cluster algorithm at the beginning.
Yes. Fuzzy C-means and particle feature extraction part is the VGG16, and the clustering part is done by the fuzzy C-means.
Yeah, the soft clustering, you mentioned FCM. Can you explain me why this soft clustering and how is better than a simple
K
K
means.
nearest to neighbors.
K means okay. Actually, we have performed several tests. Actually, and we could perform an ablation study, but ablation study is missing in the paper. But anyway, we can say that this soft clustering is better than the classical methods in our case and in the general case, generic classification case. So we have applied k-means and other methods, and we have seen that soft clustering FCM is better than all. So we have used FCM. This is fully experimental.
Can you explain me what's this soft on this soft clustering? Is the boundary a superimposed state or something?
Actually,
sure.
I have used it as a black box, so I don't have the exact details of the algorithm. But this by soft clustering, it means that the belongings have some values, and these values can have similar values that in the final we have a probability distribution, and this probability distribution sums up to 1.
Thank you for question.
Thank you.
Answer. Maybe I have also one question.
Okay.
Could the proposed tool be adapted for other medical conditions or application, maybe?
Yes, can be applied. Actually, in the generic classification part, we have used 8 datasets, and in these 8 datasets, there are also medical datasets. Like in the 8 datasets, we have survived SPECTEF heart disease prediction dataset and like other datasets. That these are medical datasets, and so it can be applied to other cases, and maybe the computer vision part can be applied to other cases too. Other illnesses too.
Sorry?
Maybe it can be applied to other visual contexts of illnesses and sickness too.
Thank you. Thank you very much.
Thank you.
No other questions? Thank you again for your presentation.
Thank you.
The last presentation of our session, detection of USA through the application of deep learning on polysomnography data, will present Khalil Ibrahim Kosar from Turkey. He's online and ready.
Hello everyone, my name is Recep Sinan Arslan. I will present my paper, which is the title of Detection of Obstructive Sleep Apnea through the Application of Deep Learning on Polysomnography Data. Our keywords is apnea, sleep apnea, deep neural networks, classification, preprocessing, and sleep disorder process. My outline as follows. I will firstly give the background of the sleep apnea detection, and then main contributions, methodology, experimental results, discussion, and conclusion. Firstly, we need to look at the problem background. Polysomnography (PSG) is a test in which biophysiological changes during sleep are recorded through the different channels. This test is the gold standard for sleep disorder rating. Scoring of the sleep stages was first proposed in 1968 and was revised in 2012, and this process was made a standard by the AASM, American Academy of Sleep Medicine. In this paper, according to AASM standards, EEG, EOG, chin and leg EMG, airflow, respiratory effort, oxygen saturation, thorax, abdomen beds, snoring, body position sensors, and pulse oximeter sensors will be collected with the help of independent channels, and the decision support system will be developed for automatically detect the sleep apnea by processing this collected data with deep learning. Main contributions of this work are the the acquisition of the original and diverse dataset from the sleep laboratory at the Department of the Chest Disease of the Pathak University. This dataset includes sleep data from 50 patients, captured through 19 distinct sensors, offering a comprehensive overview of the sleep patterns and disorders. The uniqueness of this dataset adds value to the study by presenting real-world scenarios and allowing for more accurate and relevant model training and testing. This study contributes by showcasing the successful application of deep learning techniques, specifically deep neural networks, in the field of sleep apnea detection. The utilization of DNNs offers a novel approach to accurately classify sleep disorder cases, enriching the landscape of diagnostic tools available to healthcare professionals. By achieving an impressive accuracy rate of 96.48% in sleep apnea detection, this study contributes to improving the diagnostic accuracy of the sleep disorders. The proposed model's ability to consistently deliver accurate results across diverse patients profiles reflects its potential to enhance clinical decision-making and patient care. Our methodology is given in figure 2. Firstly, we need to collect a big data set, big PSG records to train and test our DNN model. The sleep dataset was provided by the sleep laboratory from Pathak University. The sleep data collected comes from patients of different ages and genders. Their general distribution has been determined to occur depending on the number of patients coming to the hospital and the prevalence of the disease in the community. No patient selection was made regarding a certain age and gender in the creation of the dataset, and it includes the data of all patients admitted to the hospital within a certain period. In training and testing stages of this study, data from 50 patients were employed. There are 761,000 apnea records, approximately 1.8 million hypopnea records, and around 226 million normal records for 50 patients. This is a big data, as you see in the records numbers. And then there is a big work on preprocessing of this big data. The initial and most extensive phase of the work involved gathering sleep data and having it evaluated by the specialized sleep doctor. For this research, sleep information was collected from 50 patients who visited the Pathak University. Data was captured using 19 distinct sensors, including 7 EEG, 3 EMG, 1 ECG, 2 eye movement, 1 SpO2, 2 chest effort, 1 thermistor, 1 pressure sensor, and 1 body position sensor. These sensors were used to comprehensively assess each patient's sleep pattern and conditions. Subsequently, the manual evaluation of obtained data constitutes the subsequent stage in the data preparation process. The involvement of the sleep specialist doctors in this step is essential, given its utilization in the learning model. The responsibility of conducting this phase was undertaken by doctors involved in the study. And DNN model, this model is primarily built upon the deep neural network method. The DNN method allows for the thorough processing of data, this big data, aiding in better comprehension of the intricacies and features of the sleep data. Consequently, it becomes possible to detect and classify the indicators of the sleep disorder with greater precision. The flexible structure of the DNN method, owing to its ability to capture deep relationships and patterns within data, particularly empowers us to attain effective outcomes in such intricate and multidimensional datasets. During the training phase of our model, the DNN method's learning capacity has been enhanced through the utilization of vast and diverse dataset. This enables a better learning and understanding of the wide array of features embedded in the sleep data. The model has one input, hidden layers, and one output layer. The number of neurons in each layer is already shown in the figure shown below. There are 64 neurons in the input layer, 32, 16, 8 neurons in the hidden layer, and 2 neurons in the output layer, respectively. ReLU activation function is used in the input layer and in the hidden layer and sigmoid function activation function is used in the output layer. Atom was selected as optimizer. Uniform was used as the kernel initializer. In order to avoid overfitting in the model, early stopping is performed and any dropout layer is used. The DNN determination of the structure of the DNN model and parameter selection, the grid search algorithm is used and automatically select the parameters at certain intervals, and the selected values are given in table 2. And the result. In the study, you've been analyzing the average, maximum, and minimum outcomes values obtained for the proposed two-layer classifier design developed using the deep learning model for 50 patients. It's evident that the suggested model outperforms other classifiers in terms of all parameters, including accuracy, precision, recall, and F-score. These results include the highest and lowest accuracy rates among patients, as well as the average accuracy across all patients are comprehensively presented in the table 3. Thanks to the utilization of deep learning models in the context of the deep learning, the proposed model has gained the ability to extract complex features from the data. This ability is crucial for accurately discerning subtle differences between cases of the sleep disorders and normal conditions. As a result, the model through its enhanced capability to understand subtle variation and patterns within the data, it achieves higher precision, recall, and fast score values. In terms of the accuracy, the proposed model demonstrates exceptional performance across different patient scenarios. For the patient achieving the high accuracy, the model achieves an impressive accuracy rate of the 98.35%, alongside northward precision recall and score values of the 98.95%, 97.74%, and 98.34% respectively, highlighting its proficiency in accurately identifying sleep disorder cases. Even for the patient with the lowest accuracy, the model maintains a commendable accuracy rate of the 93.20%, showcasing consistent performance. This robustness is further substituted by precision, recall, and F-score respectively. When considering the collective patient group, the model's performance remains strong with the average accuracy of the 96.48%. These outcomes underscore the model's reliability in consistently delivering accurate results across diverse patient profiles. The confusion matrix accuracy loss area of the curve for patients with the highest accuracy rates obtained through the classification of apnea using deep learning methods are presented in figure 3 to 6. You've been examining the confusion matrix in figure 3. It can be observed that the design model misclassified some apnea patients as non-apnea, but accurately distinguishes non-apnea cases. When examining the accuracy and loss graph provided in figure 4 and 5, a consistent pattern of the change in accuracy and loss over time is clear. Considering the test results of the study, it's evident that the proposed model does not suffer from overfitting issues during apnea detection and consistently achieves high levels of the accuracy. Furthermore, the design model underwent early stopping during the training phase with an early stopping value of the 32 epochs. This was implemented as a precaution against overfitting and to enhance the model's generalization ability. And discussion. This work focused on the application of deep learning methodologies in the field of sleep apnea detection. The result of the study highlighting the effectiveness of the DNN-based classifier design in accurately classified sleep apnea cases. Deep learning architecture, specifically DNN method, proved to be the suitable choice for this study due to its ability to learn complex and high-level features from complex data structure. The potential of DNNs in the field of sleep apnea detection is encouraging advance in this field. However, the limitation of study and area on which future research could focus should also be considered. Over the last decade, numerous studies have focused on detect sleep apnea, with research continued today. Table 4 highlights selected of these studies. Analyzing reveals that recent research predominantly utilizes various datasets. Classification tasks are typically performed in pairs using algorithmic solutions, mainly relying on machine learning and deep learning techniques. The classification performance ranges from 85% to 97.21%. And conclusion. In this study, we explored the application of deep learning techniques in sleep apnea detection. Our aim was to develop a robust decision support system for accurately identify sleep disorder cases. Leveraging deep neural networks, we focused on effectively distinguishing between normal sleep patterns and sleep apnea instances, thus improving diagnostic accuracy. Through meticulous data collection and analysis, we demonstrated DNN's potential in capturing complex sleep data patterns. Our results highlighted the success of the DNN-based classifier, achieving an accuracy of 96.48%, surpassing similar studies. This study contributes to sleep medicine by enhancing early diagnosis, which can significantly impact patient outcomes. The use of deep learning enables precise pattern recognition, promising advancement in real-time monitoring applications. Ensuring model interpretability through explainable AI methods is crucial for medical practitioners' trust. Clinical validation and longitudinal studies will further refine the model for real-world medical settings. Thanks for listening to me. Is there any question? I can also answer your questions.
Thank you, Mr. Arslan, for your presentation. It was very nice. So, are there some questions from audience?
Regarding your data set and the experimental protocol, I have 2 questions. I don't know if you participated in the data collection, said it was in the hospital, right?
Yes.
I have worked with creating these protocols for electromyography and electroencephalography, and the volunteers for this experiment often said after an hour or 2 using these devices to feel some discomfort or itching. I would like to know to what extent you said you use electrooculography, electroencephalography, electrical myography, and the other, I don't know, 4 sensors. To what extent this measurement with different electrodes on the person's body affects the quality of sleep and can also influence your data set in a way that they would usually wake up during the night with some issues that can lead to some problems on the data set. And how the, for example, electrooculography that have to put on the eyes of the person, how is it done for them to sleep? Because the cables on the face and everything, it's really uncomfortable.
Okay. First of all, the PSG is a gold standard for detecting the sleep apnea or this kind of sleep problems. So if you have a sleep problem, you have to go to a hospital and a sleep doctor analyze your problem and say that you need to sleep our hospital one night. We record your recordings as a ASM standard, and we collect 19 different sensors, and I will analyze your sleeping, how you sleep in night when you sleep in the hospital. I will record your sensors data, and I will analyze the sensor data, and I will say that you are a sleep apnea or not. So if you will not sleep in the hospital, the sleep doctor cannot define your problem. You have to sleep in the laboratory, and you have to the sleep doctor have to collect your data. So if you wake up in the night you need to sleep one more night. So you will sleep at the beginning and you go when you wake up. So almost 6 hour sleep, we need to collect your data. So if you sleep 3 hours, 2 hours, or 1 hour, we cannot collect your data. So you need to sleep one more night, almost 6 hours in the hospital. And we will collect 19 different sensors and analyze to detect your health problem.
Okay, thank you very much. Are there any other questions? Okay, thank you for your presentation and answers for question. I think that we can close this session. I would like very thank you all participants, presenters for the presentation. Very interesting. Also, many thanks our technical guys and support. See you on the next session.